Okay, thank you very much, Chris. Sorry we have a little problem, so I'm going to move right ahead. You know, as you heard, Chris drilled, and remember he had this presentation where he was drilling and he said he's creating Swiss cheese. Now, that Swiss cheeses are full of very nutrients and all kinds of good stuff and good smell. You know, it's not just the holes are just part of the whole thing. So I'm very offended, of course. But let's move on. I think Laurent Sibyl has given me a good introduction, as you will see, about my topic, what are we doing at the UNSW? We are interested in solar energy, we are interested in construction, and in mining. And specifically mining because when I came here to Australia, I thought this is the best place to do mining research because you have all these great miners around. So, but we are also really interested in going on, you know, because we have Aaron, my assistant, is really coming out of Hunter Valley, so he wants a vineyard up there, of course, and you're going to have. And he, Phil didn't have that as an export, okay? Lunar wine and lunar beer, of course. Asteroid beer, yeah. And we were sitting next to a Scot somewhere at the conference. He obviously wants to have a distillery right there also. So anyway, that goes with our interest. So we also, for the visitors we have here, Phil talked a little bit about history, and I also look at history a lot, and this is Sydney in the early stages, of colonization. And I want to just tell you a little story. When Cook was doing prospecting, he didn't go on land. He was forced to go on land because you're on the ground, and he made a big hole in his ship. So they had to, you know, close the ship with the lumber there, with the wood there, and he got to know some people. But across the coast, he never went on shore. He just made big, you know, drawings and stuff. They're great drawings. It looks like from a prospector or from a satellite going around the moon. Very nicely mapped. It's beautiful. But he made a big mistake that almost was deadly. It became deadly. Because they came back, the first fleet, with the knowledge that he had created. And, you know, it's a prospector going around Mars or whatnot, or going on the moon. And all they had was pictures from afar, drawings, except at one place up there in Queensland, probably, where they were on the shore or on the ground. And this is a significance down here, but because they needed to come back and they wanted to build housing, bridges, with the wood, with the lumber that was available. And they, from the picture, they thought, you know, it looks like British lumber, British trees. But they were not. They were eucalyptus trees. And too bad, yes. They didn't bring in any forges. They didn't spend some saws. So their axes and their saws, you know, go blunt, and the axis actually broke, and they couldn't fix it, and that was it. Okay, and you know the story about they didn't have any farmers, no farmer with them, so you couldn't grow grain because they didn't realize that the soil has to be a special way to actually grow something. So, and they almost died. The whole thing almost died because the second fleet was delayed by a year, almost. So, great story to learn about living up the land, ISRU. And you need to know, you need to have the right tools, not just want to do it. And they need to work, and they need to be tested, not just going and having a look, or in the Simulant and here. And we asked, Laurent, I asked him about how would you go to think that you have to go to the moon and test it. That's exactly. You cannot just do everything here. At the end, you really need to know, do they work? and we need to collect the data. Remember this one, I'm sure. The rover got stuck in the powder, and now we got stuck on Earth too, right? That's a big problem. We have developed some technologies, but we still get stuck. But that more from stupidity than technology. Australian Simulant, okay, we talked about that. Now we have to change our name. We can't call it ALS, this is Arizona. So you have to come up with something better than that. You saw it outside, but there's not just Simulant, there's also rock, okay? And there's Tracy's rock, it's called the famous Tracy's rock. Very cool looking thing, and here. But in the back you see how immense this regolith is. And we don't even know the depth. It's some 40 meters, 100 meters in certain areas. It's a massive amount of regolith laying up there. Okay? The mechanical properties we heard about. We need to deal with it because we're going to have to build tools. And you heard about the powdery, you saw it out there, how powdery it is. And so we also have to make a simulant. And obviously there are some unique properties because of the situation of the moon. If the moon is exposed, there's no atmosphere. So lithium meteorites, small meteor hit the surface in I don't know, 100,000 kilometers an hour or something. And it vaporizes, some vaporization, but then also creates this agglutinate. It binds the stuff together. You saw a picture before, and I'll show you another one. This is a very unique situation which we can't recreate on Earth. We can't find agglutinides on Earth. We have to make it. It's not easy, and it's very expensive. And they are very important parts of our simulant. I don't have them out there because I'm poor. This is one of them, okay? This is an agglutinide. Very, very ugly, right? And those are the ones that scratch, that the astronauts, the spacesuits and whatnot, almost scratch through it because of them. Okay, not of the round one, the glasses per se. But as you can see, it's a lot of silicates, some oxide, and ilmenite you talked about before, where you have oxidized.
Scale?
Huh?
Scale of that program?
Ooh!
The micron to
Yeah, 100 microns. They are different sizes, about from 10 microns to 100 microns. There are a couple sizes, yeah. You find this online, they analyzed where is the dust of the soil on when the astronauts came back, and we talked about it, they fell on their faces a lot, right? Because remember that they did this and it fell right over, so you got the whole thing full, and then in the back, and then if you look between in the legs or here, they had it all abraded and almost through from those agglutinides. Nobody expected. So you can look that up. It's very dangerous, and I'm sure you have heard about this, about dust and what it can do. And you have to be very careful. You have different chemistry. This is our Apollo 11, 12, 14, blah, blah, blah. You heard about the Mare, and they're from different places. But we can look it up, silicates, okay, oxide, and then and there's the iron oxides. And with this one here, we can make glass, okay? That's what we use on Earth to make glass. And I have a lot of it, 42%, 46, a lot of that stuff. That you can easily, we talked about making fuel and other stuff, but I want to do construct. I want to do things, right? And also the H is actually in the soil between the particles. The H you can just, it's called a volatile. You can just suck it out. So you can get O out of here, and you need to get C to make C with H. We can make polymer on the moon. Okay, that's what I'm interested in. So I have to find the raw material. and you find the raw material, because it's a basaltic stuff, we had to look around New South Wales, and we found this little speckle up here, okay, that has a basaltic material. So we went there, we looked at it, and we drove, and we found there was a quarry run by Hansen. That's a big part of the Heidelberg group. It's a huge concrete group all over Australia. And they run this quarry, and they had the material we wanted. We went there, that's how it looks. It's an old, like a chimney coming from deep, deep out in the earth. An old that has abraded, but it's like a chimney of basaltic material. And as you can see here, these has a special form. They are not packed together nicely. They are broken up because of the temperature when they created. They broke apart in a five octangle, or yeah, something like that. And you find that same thing in Ireland, by the way. The Giants Walk, where they are huge, these things. Anyway, here we go. We took the final stuff. Here's then a comparison of our ALS with the Apollo 11, Apollo 12, and we look at differences, the chemical differences, okay, and they are, pretty close, but, let's see the FE2OC, that one, you can't find anything on the moon, okay, I think none of them, but instead they have the FEO, right? And so it has to do with the amount of oxygen when it's created and the amount of heat. So it's different process that has happened. So we're pretty close. Now we need to get the distribution, size distribution, and there is from the Apollo program there is a max and a min. And as Laurent said, you can't do it all in one shot, so you have to pick yours. So we go with the red one right smack in the middle. But what was interesting, down there at the very fine end, they all stop showing. This is very important down here. How's the distribution? How much is there? But they're all stopping. It's because it's very difficult to measure. Okay, so we did an analysis of our dust. And we can now copy this in for the very low end of the spectrum, and then we go on with adding more material. So what you see out there is this soil. We didn't add the big particles yet. We have it in the over there, but we thought you would steal it and just walk off with it. So we didn't add that to it to make it nice. Good. The first thing you heard about, we are interested in the thermal energy storage, and we use that concept you just saw with the body, the thermal body or lunar body. When you have sunlight come, you heat a basaltic or a rock, or what we created a sintered rock down there. We heat, and then you saw then the rovers, you park it on there, and then you close it, you bring the upper wing down and close it for the night. Because heat goes away only through radiation. Okay, so if you make a house over it overnight, nothing goes through. And the rovers are going to stay warm and protected. So that's the kind of the temperature idea we have. We're going to take it a little further. We have this, we're going to call a thermal battery. We have multiple solar what do you call them?
Reflectors?
Reflectors, yes. Reflecting onto the thermal battery. And then we use gas to run through the battery when we need it in the night through pipes, and we heat up different items or different cells. 1D would make heat. This one is electricity generation, and then space heating. And as you can see, we would like to recycle some stuff and then bring it back in there. Also, maybe when it's still hot, to bring the energy back. So that's kind of the idea. So our Aaron has started with sintering and melting. The same material you see out there, we bring about 1,000 degrees, okay, over 1,000 degrees, and you can melt it down to becomes like a basalt again. And then we were interested how do you do that, the temperature, how you ramp it up, how temperature needs to be, so you don't get any cracks. You don't want cracks in there. You want to have a nice solid piece. So we were playing around, or he was playing around, trying different methods and concepts. And then he came with some results, specific heat capacity, density, stored energy, and supply. And this looks pretty good. And now we're going to go bigger. And one thing we want to do is to look to maybe use the 3D printing to actually make this battery in a certain way, the way we want it, with maybe openings inside where we can push the air through, and when we need the heat to generate electricity. So this is still, that's a work in progress, okay, as everything else is. Second one is we want to have mining technology that's designed for the moon, okay? And as you saw those pictures, these are the first miners, so to speak, right? They had the little tools to drill in there by hand and pick up soil for sampling and whatnot. So we wanted to do a way that you can actually go deeper miner. You don't want to do it just on the surface. The surface is very, very loose. As you can see, you can dig it very nicely, simply. But if you go below 20 centimeters, it gets rock hard. It's not rock. It's just rock hard. Very, how we call it, 100% relative density. And the way we had to make it, that was in the 80s, I had to take a huge press and put it into that bucket you see here, put the soil into that bucket, and then weight over it, and I had to press it with full force to get the density I needed that to replicate the soil on the moon. It's not the top, the bottom, that's where I have to go through. So then I did try to use excavator. Guess what happened with my excavator? You know, digging, couldn't dig anything. Unless you have a really strong force, you know, and that's what we don't want, because really strong force needs not only energy but joints and heavy weight and all that kind of stuff. No. So that's what I did then. Use explosives. I looked at explosives. It's a very, very good source of energy in space, very safe. Put it in. It's like we can lose, just pop the soil a little bit, like, poof, okay, so we can dig it, and it worked. But it also creates a crater that you don't want to do, right, on the moon. You don't want to create a dust bubble, dust thing up there, looking like a huge mine. No, that would not work. And so you have to put this on the ground, deeper to see if, and yet, as you can see here, I got a nice, made a nice little crater, right, in an inner chamber with my explosives. So we dug it out and look what happened. And then we measured the energy. We needed to dig it out with the backhoe, measured forces in the moon. And we got about a 40% reduction in energy using this method. Obviously not good enough, I think. So I thought, let's use something else. And I'm working on underground utility detection and digging, underground utility. Lots of accidents in the world, almost every day, not almost, every day. Backhoe hitting cables, gas lines that blow out houses, everywhere fires. It's unbelievable. One method to protect it is, I use ground penetrating radar, but this is another one where you drill a little hole. No, you don't want to drill. This is suction. Okay, that's a vacuum truck, right? Has a little pipe there, and then you make a hole until you actually see the utilities. You see here one that's probably a gas line, down there a deeper line. So you want to see, and that's a suction mechanism on Earth, and to see, to verify the position. So, okay. So then I remember good old Venturi, where you have flow of gas or water through pipes. and when you get it from a larger diameter into a smaller diameter, you get a difference in pressure, low pressure, high pressure, and the difference you can use as vacuum, right? From the side in. You can have a little pipe coming in and you can draw air, and you probably have seen that in chemical labs. So that's a cool thing I could use. So I applied this and say, okay, if I put a pipe into the ground and push in air and have a little pipe going out of it, make a little hole in the soil, I can create a Venturi effect, and that is, here is low pressure, high pressure. So this high pressure pushes the stuff up and sucks the soil right with me, and it worked like a dream. Whoa! They are actually using that pneumatic transportation. That is grain. That is being there is a little vacuum machine in there. 1 atmosphere, high pressure. You create an under pressure under there, and it just pushes the grain right in. At 1 atmosphere pushes the grain into the pipe, and that is what it's called a cyclone, and then it pushes it right up there and into the truck. Cool. So that's what I want to do, and actually there is a science about this, pneumatic transportation, pneumatic conveying it's called. There's all kinds of things you can, depending on the density, the grain size, you can do it. It's a very cool technology, very little known. So I built my system, mining system. Here is the soil. Here is the that little air going up, coming over here, a separator, dust filter. Here's my little air blower, and then puts it right back in. Okay. Here is the nozzle in the soil. The only problem I have, I need to create a compression, compressed air in down there, because the lunar surface is vacuum, right? If I start, you can't do vacuum. You need to create your pressure, artificial. So I have this little packer, it's called, in that hole, you see that there? This sits down there and locks it off. There is no air going out. Now I can push the air in up here. I push the air in, it goes down. There is the packer, and it comes out with the pipe, and I'm bringing it over here to my filter, and I'm putting it back out. And it works like a dream. Whoops. Okay, we're looking at different holes we're creating. This is a look down into the mine. Obviously the soil in the pipe. And then we looked at different holes, different depth. And this is because we had to take the pipe back out and things fell down. So we're looking at productivity, production, and then we're going to look at different pipe sizes and so forth. So there's all concrete. We heard about that. This is concrete on Earth. We are using concrete that is mixed with the Simulant. It's a little bit of polymer powder mixed with the soil. We put it in our form. We then fill it up, compress it, put it in the heater, and then we have things like this, compression, tension. And here we have, obviously not as big as I want, and I don't want to talk about this. This leads to a new thing. It's called self-healing concrete. We make bigger ones with a bigger, different approach and mechanical to create more pressure. See, this opening is now bigger in the middle, but we need to go even further. This is for my approach for landing pad. Remember, I have a weaving fiber, glass fiber woven that I lay down, and then I put my polymer concrete over it, and I would then drive continuously, make a good bed, road bed in the front, take the material from the front, and then put it right down, hook it, and move on, and have this thing make a continuing thing. Roads, these are Roman roads, right? Roman roads have multiple layers, not just one layer and then the top, okay? If you sink to the top of the soil on the moon, it's going to crack. You need a support underneath, okay? That's what the Roman did. That's why they had good roads. and this is before the Roman, okay? You can't have that, right? You can't have, otherwise you're going to have this, the rotten stuff, if you don't do anything. But we have cableway. This is very difficult to do, but we have cableway, okay? So in the 90s, I proposed this, a cableway that, with cables that I can loop sideways. And here is for lunar lander, 1,200 meter span. And I looked at the dimension of the cable form. You can loop things sideways. Okay, you can cover a large area when the lander arrives. You can put it down, and then you can lift it back up. I also this is my solution to how hook onto a Eitokava, to an asteroid. You know, a little clamp, just a teeny little clamp. You let it down, grab some lock, and then just pull it up. No anchor, just grab something, like a clamshell. That also would work really well for the moon. I tested it. Very lightweight, but right now it's not. So that's my lunar trainway. That's a thing done by I want to close with some kind of going back. I have worked on robotics. This is my robot excavator. It was very smart, much smarter than our excavator. It could dig and detect and move around rock and make a picture of the rock. But nobody's interested in that. So I made it in a remote control. So this is with 3D, and it is unbelievable. And actually, in year 2000, I was here. In year 2000, I controlled that echo from here, from UNSW, during the Olympics. I was here during the Olympics. And here's the TV station. I did the whole thing live. So with that, I want to close. This technology also applies, obviously, to control something remotely on the moon. But we can do robotics as well. Thank you.
Thanks very much. While we're switching, maybe there's time for one question. Yes.
How much carbon is on the moon?
A lot.
Lots.
C, yeah, but it's chemically bound, you know. Yeah. I'm not a chemist, okay? It's going back, NASA guys told me you can make carbon. I would like to collaborate with somebody to actually try it. Yeah. I don't know how to do it. Anybody else? Carbon? Okay.